Hello, welcome to this series of CH103 lecture. This is now on chapter 17, and we are beginning on our discussion on spontaneity, entropy, and free energy. So we're going to look at these topics in this chapter, starting with this video, which I plan to cover the first three: spontaneity, entropy, and the effect of temperature on spontaneity. So in thermodynamics, we've already covered some introduction from the first law of thermodynamics. And the first law, we know it states that the energy of the universe is constant. So in other words, this is the law of the conservation of energy. Energy is neither created nor destroyed, but can be transferred from one form to another. Here in the spontaneous process is something that is going to be added to this law, and we are going to define that more and more in detail as we go. This spontaneous process, by definition, means some event that occurs without external intervention. So very important, spontaneous process doesn't mean very fast. In thermodynamics, it means it occurs without any external intervention. So a spontaneous process can be either fast or slow. Now let's do the comparison here between thermodynamics and kinetics. We've studied kinetics. Kinetics basically deals with the rate of reaction, and it depends on the pathway from the reactants to the products. So if you're looking at the reactants here, this is the energy diagram. That's the energy, and this is the reaction coordinate or reaction progress. So what we have here, the energy of the reactant is at a higher sort of energy. Let's take this as E1. E1 has a higher value of energy compared to E2. So if you look at E2, when the product is formed, has a lower energy. In fact, when we are dealing with the reaction, if this energy is lower, that means you have delta E of energy that is given off. The delta E of energy is negative, that is released, and this is called an exothermic reaction. All right, so those are what we have looked at in terms of energy of chemical reactions. But this region and the region that are colored sort of greenish blue here are the energy related to what we study in thermodynamics. However, the middle region, which is the purple region here, is essentially the domain of the kinetics. So we see here that there is a amount of energy required to overcome, which we know this energy barrier is called the activation energy, EA, activation energy. So the higher the activation energy, the slower the reaction, or the less products that is formed. If it's a low activation energy, a lot of these products is formed. So that's in kinetics. In thermodynamics, it provides us with the information on whether the reaction is spontaneous based only on the properties of reactants and products. So in other words, the idea of spontaneity is just based on the properties of the reactants and products in terms of their energy status. That's what we will be looking at. So here we come with this term here, entropy. Entropy, okay, yes, sorry, I got interrupted a bit. So now let's continue. Entropy, which is given the capitalized S in the symbol, this is a thermodynamic function that describes the number of arrangements that are available to a system existing in a given state. Now we'll try and go into a bit more detail of this meaning here. That's a thermodynamic sort of definition. What essentially saying is that if a system has the possibility of multiple forms of arrangement in that state, it's going to be a favorable. In other words, that's what we are looking at in terms of spontaneity. But the more generic definition, which is very basic and maybe a lot easier to begin with, is this one here. Spontaneous process or entropy is defined as the degree of randomness. The degree of randomness. So let's go into the slides to explain this. Look at an ideal gas in an evacuated bulb. So if you have a dual bulb here with a valve, a stopcock to separate the two different regions, and you have a vacuum system and you have ideal gas in one. As you open this, naturally this is what we expect, and this is what happened. The gas will distribute itself evenly. So this process here is what we call a spontaneous process. So nature spontaneously proceeds towards the state that have the highest probabilities of existence. So when this gas becomes evenly distributed, the probability of distribution is a lot higher here compared to when it was here in the just one arm of that bulb. So let's look at it in terms of the micro state level. So we're looking at it in a bit more detail. In this time, let's look at 4 atoms here, or 4 molecules, and see how the arrangement in the 2 balls. These are the possibilities that we can get out of just these 4 balls, 4 spheres. So here you will see 3 and 1, 2 and 2, 1 and 3, and all 4. Now, how it is going to come to either one of these depends on the probability of reaching that state. So each configuration that gives a particular arrangement is called a microstate. That's a microstate. So this is a microstate, this is a microstate, and likewise the rest. The probability of occurrence of a state depends on the number of microstates which the arrangement can be made. So in other words, whichever has the highest probability, that most likely is where the molecular arrangement is going to be proceeding to. So let's look at this in much more defined sort of detail. So if you label these spheres in the bulb A, B, C, and D, there are 4 of them. And these are the possible microstates. So in this one here, where all the spheres in just the left arm, there'll be only 1 possible microstate there. The probability is only 1. Here, if you have 3 and 1, you look at all the possibilities of the 3 and 1 altogether, it comes to 4. Now let's continue with this and look at 2 and 2 on the bulbs. This combination relates to a total of 6 microstates. I hope you can see, because here you have A, B, C, D, and here is A, C, B, D. So you are taking all the different combinations, which is the possible arrangements, to give you the total number of microstates. Likewise, so the 3 and 1, so in this time is the reverse of the one that we started off from the top, so it's still 4, and likewise this one is still 1. So out of this arrangement, you see that 3 gives you the most most highest level of microstates in its probability. So this is what we called positional probability. So this depends on the number of configuration in space that yields a particular state. For example, in that microstate number 3, there was the highest number of configurations or microstates. Gas expands into a vacuum to give a uniform distribution. When it's expanding to that vacuum, the expanded state has the highest positional probability of states available to the system. So let's take it to an example of water. Water is a solid, a liquid, and a gas. So if you look at this, in the solid phase, you have fixed atoms or fixed molecules, and the degree of probability in this is not that high, and it'll be a little bit more for this liquid state, but much more when it is in the gas state. So in other words, the positional probability in the gaseous state is a lot greater than in this liquid and also in the solid state. So what we're saying is that the entropy of the solid is lower than that of the liquid, and it's much lower than that of the gas. What about in a solution? In mixing compounds to make a solution, or solution of two liquids. Entropy change when mixing two pure substances is expected to be positive. So we expect this to be positive. The reason is that there is an increase in the positional probability, and likewise there is an increase in the level of microstates. So this results in the presence of more microstates for the mixed condition. When this happens, it is caused by an increase in volume that is available for a given particle to be mixed or to be around. So here, owing to the increased volume available to a given particle after mixing occurs. So formation of a solution is favored by an increase in positional entropy, and that is associated with mixing. Now let's look at these two examples here. First one, choose the substance of a higher positional entropy, solid carbon dioxide and gaseous carbon dioxide. I think this one should be obvious, because in the solid carbon dioxide you have less positional probability and less positional entropy. So in other words, this entropy of solid will be a lot less than that of gaseous carbon dioxide. What about in this one? Nitrogen gas at 1 atmosphere and 1 times 10 to the power minus 2 atmosphere. So if you're looking at here, the difference are the pressure. So here the pressure is 1 atmosphere and here is 0.01 atmosphere. So when you're looking at 0.01 atmosphere, you are expecting this to be higher in volume. Higher in volume. So if this is high in volume, this is less in volume. Less in volume. Because of the pressure, increase of pressure. What you would expect is that there is a greater positional entropy or positional probability here compared to that in the 1 atmosphere. Okay, so these are already answers that we've explained. Now let's go to one here that says sugar molecules. Let me read this one a little bit more slowly. Sugar molecules become randomly disposed in water when a solution forms and thus have access to a larger volume. and a larger number of possible positions. So in other words, the mixing, which is dissolving of sugar in water, is actually increasing the entropy because there is a greater increase in the positional entropy or positional probability. So here it is. Positional disorder is increased and there will be an increase in entropy. Okay. Let me continue with the next slide. Let's continue with the next slide. What about this example here? Gaseous iodine is changing to form a solid. So when you have iodine gas, I2 gas, and that changes to I2 solid, this is very different from what we've been discussing so far. What we see here is that this is a higher degree of disorder compared to here. This is a less degree of disorder. So in other words, the positional entropy or positional probability here is going to be less compared to that in the solid. So this is a very opposite of what we are defining as a spontaneous process or a increasing of entropy. So this process involves a change from a relatively large volume, okay, to a much smaller volume, results in the lower positional disorder. So the entropy here is going to be decreasing. S becomes lower. So what happens in here? I mean, what we're saying here in thermodynamics, what we're going to say is that the entropy of the system favors the disorder. So what is happening in here? For this process, delta S is negative, implying that the entropy decreases. So that's just a repeat of what I've said. Let's look at that. So what we are seeing, there are some positional entropy that we see is increasing, and there are others that are decreasing. So what is the summation of this situation that we can put together? This comes into the second law of thermodynamics. It says, in any spontaneous process, there's always an increase in entropy. A spontaneous process involves this, an increase in entropy. So what we are going to look at is this. The entropy of the universe, which is this one here, is actually the sum of the entropy of the system and the surrounding. So what we were discussing previously, as you realize, some of the positional entropy looks to be increasing, like when the gas distributes itself into the two bulbs, or when it's changing from liquid phase to gas phase. That's an increase in entropy. But if you look at some system, for example, like iodine, if iodine solid is forming from iodine gas, that's the opposite, and that means the entropy is decreasing in that. So how do we explain it if this is not a spontaneous process? We're going to look at it in this holistic context. In other words, the entropy of the universe, that is the change in entropy of the universe, is essentially equal to the change in entropy of the system and plus the change of entropy in surroundings. So we have to look at both of this in order to understand this this behavior in its entirety. So this is what it can be summarized to. The entropy of the universe, the change in entropy of the universe is positive. That means the entropy of the universe increases. The process is spontaneous. Okay? If the change in entropy of the universe is negative, that means it's non-spontaneous. Okay? Non-spontaneous. And another way of putting it is spontaneous in the opposite direction. So if it's negative, it's non-spontaneous. And the other, when the change in entropy of the universe is zero, that means the system is at equilibrium. So we'll be looking at all this sort of changes in the forthcoming slides. Now we've looked at the example of iodine changing into solid from gaseous state. Now let's look at this one here, in a living cell. In a living cell, you see that large molecules are assembled from simple ones. For example, like you start with amino acid. I'm just writing the amino acid. Okay. Amino acid are individual carbon-based molecule that will combine together to form proteins. So in other words, this single individual amino acid molecule, so many of them, will be connected together to give you the entire structure. In fact, this is what we call a polymerization or polymer. A protein is a polymer, and you hear the word that is called polypeptide because of that. Polypeptide. So that formation of a large molecule comes from all the pieces or all the individual units. Here are the amino acids for that. So if we look at this in the detail of thermodynamics, what we are seeing is this: the process, let me go back, the process, this process here involves the decrease of degree of probability or decrease in entropy. So decrease in positional entropy or positional probability should decrease the entropy, and that means it's negative. Yeah, let me just quickly write. It's negative. So if the entropy is negative, it's non-spontaneous. However, these processes are happening all the time. We expect it to happen, otherwise there's no life that will be supported. So what is the reasoning behind it? Now, what I've said before, let me reinforce it again, and that is this. In the entropy of the universe, you have the system and the surrounding. So in other words, you have to consider the system and surrounding together in order to fully understand what is happening in the entire process. So you cannot just look at one entity like system alone and expect that to have the full picture. So you have to have both. And that is the reason why we need to break it into those two different forms of the entropy. And so the cell process is something of this sort. Although we look at the entropy of the system to be negative, we have to also consider the surrounding. Because if the surrounding is a lot larger, it can result in the overall positive. So how do we determine the entropy change of the surrounding? Now let's look at that in this section here. And you will see that entropy changes in the surrounding is determined by the flow of heat, and that is based on whether the process is exothermic or endothermic. So this is what it comes up to. In exothermic process, it is important driving force for spontaneous reactions or spontaneous process. So the impact of transfer of energy as heat to and from the surrounding is greater at lower temperatures. Okay, we'll get into that into an equation form. Here, you look at the driving force provided by the energy flow is equal to the magnitude of the entropy change of the surrounding. So the magnitude is calculated from the quantity of heat, and that is divided by the temperature. So that's the relationship. In exothermic process, the change in entropy of the surrounding will be plus sign the quantity of heat divided by the temperature. Note the units here, usually it's in joules, and this is Kelvin. You already know the Kelvin, but note that the entropy is a lot of the consideration is given in joules. Endothermic process, again, you will see the endothermic, it's a minus sign here, the quantity of energy over the temperature. So if you look at the overall generalization of this reaction, the effect of temperature on spontaneity can be written in this form. We're dealing with the surroundings here. That is equal to the enthalpy, negative into the enthalpy over temperature. Let's look at let's look at this sign. Delta H has a negative sign, which is here. So if that negative sign, if delta S of the surrounding is positive, since the heat flows into the surrounding, so the substitution of either exothermic or endothermic, depending on the sign here, is going to influence this negative sign, and therefore that will give it the change in entropy value, as we will look at some of these examples. So this is what we'll eventually show in our discussion, and that is the entropy change of the system, entropy change of the surrounding, and the universe. So if all of these are positive, then process is spontaneous. Everything should be spontaneous. If all of this is negative, then it should be non-spontaneous. But if it's plus, that is, the system is plus and this is negative, so this will depend. If the entropy change of the system has a large magnitude than surrounding, then you would have spontaneous process. So in other words, the plus is greater than the minus, you'll end up with spontaneous process. Here, surrounding has a larger positive than the minus, it'll be a spontaneous. Remember that the condition for spontaneous process is when you have positive entropy change. So let's look at these two examples here and finish up with this lecture video. So this is iron that is used to reduce antimony in sulfide ores. Notice that this reaction here is exothermic. So we're going to use this delta H to determine the enthalpy entropy change of the surrounding. And let's look at the second one here. This is antimony oxide with carbon. This is a reducing agent to give you antimony, and this is the enthalpy. Notice that the enthalpy here is positive. So the first one was negative and this one is positive. So its question is calculate the enthalpy, the change in entropy of the surrounding for each of those reactions at 25 and 1 atmosphere. So let's look at the first one. For sulfide ore reaction, let's substitute in, that is the entropy change is equal to minus enthalpy over temperature. Temperature must be in Kelvin. And let's do the substitution in. This is minus 125 kilojoules over this. And notice I said before you should try and consider working in joules all the time. So the answer comes into kilojoules, and that is converted to joules. What is the sign here? Because of the enthalpy, which is negative, and this is negative in the entropy equation, that will give you a positive number. So you end up with a positive. So in other words, here the entropy change in the surrounding is positive. Now let's look at the second one. So substitute in the enthalpy change. This time it was positive, 778 kilojoules divided by this. There is a mistake here. There is a mistake. This shouldn't be a, that's wrong there. Sorry. So ignore this sign. That's not supposed to be in there. So you'll end up with a negative answer. And so this will give you the value. So the answer is a negative. So in other words, the entropy actually decreases, which is now what we would say non-spontaneous. Spontaneous. Okay, that concludes this first lecture on the Chapter 17, Spontaneity, Entropy, and Free Energy. Thank you.